An interesting exercise we can undertake with the Hückel method is to use it to examine cyclic polyenes and compare those results with the ones we got for the linear polyenes. So let's set up what a cyclic system looks like. I've got a set of carbon atoms, I'm going to say n carbon atoms, that are all arranged together with the nth atom in the chain connected back to the first. All right, so it's an arrangement that looks something like this, where I haven't specified n, but I will indicate that n must be an even number. All right, so how does this look compared to the case for the linear polyenes? Well, let me first, I'm going to go over here in the upper left-hand corner and construct what the secular determinant would look like in this case. So I've got alpha minus e along all the diagonal terms, okay, and that won't change. And then I'm going to connect the ones that are connected to each other in the molecule, okay, so that's going to be on either side. But in addition to the ones that I had for the linear polyenes, which are the ones I've drawn here, I also have betas that connect the first and the last of these elements, because the first and the last carbons are connected over here. So this is one difference, one area of difference between the linear and the cyclic polyenes. All right, and just as we could in the case of the linear polyenes, we can actually write down an exact solution for this, and it looks like this. The nth molecular orbital will have the energy alpha plus 2 beta cosine of 2n pi over capital N. So you can see it's actually a little bit simpler form when we have the cyclic polyene. So how does that lead to any sort of difference that we might sense in terms of the properties of these types of molecules? Well, what I want to do is I want to draw the energy levels for both the linear and the cyclic case. So we've got increasing energy over here. Now, if I had a linear polyene, I would find that the energy levels basically go up, and all of these energy levels are non-degenerate. That is to say, there's only one molecular orbital per energy level. Okay, and at some point in the middle here somewhere, that's where we've got energy equal to alpha. Okay, so they're either above alpha or they're below alpha. Alpha would be the energy they would have if the p orbitals were not bonded to anything else at all. All right, how does this change when we go to a cyclic polyene? So I'll just clarify, this is linear. For a cyclic polyene, I end up having one state that's non-degenerate at the very bottom, but then every other state as I'm climbing the ladder here of molecular orbitals are doubly degenerate. That happens too when we go to the ones above this midpoint until I get to the very top one. So if I were to count these, this would correspond to the first molecular orbital, or 0, or 2, 3, 4, 5, 6, 7, and so forth. Actually, what I get up to here at the top is n over 2. So the number of nodes that are in these wave functions, remember they increased here when we looked at the linear polyene case. We had 0 nodes for the first, 1, 2, and so forth as we climbed up. When we go for the cyclic case, we have 0 nodes here, 1, 2, and so forth, and up at the very top one we'd have n over 2 nodes. Now the question is, can we explain why these, all of the ones in here, are doubly degenerate, but the first and the last ones are not? What would that look like if we were to draw a picture of these molecular orbitals? All right, I'm going to do this in a rather abstract way, but I hope that it is one that you can relate to. All right, first of all, I'm going to imagine that I'm looking down on the top of this cyclic molecule, and I'm looking at the p orbitals that are sticking straight up. So p orbitals are sticking straight out of the plane of the board. So I'm just looking at the tops of these p orbitals as I go around this cyclic molecule. And let's say those are the positive ends of these p orbitals. So now it's these p orbitals that I need to add together to make a molecular orbital. Now the nodes that I'm talking about in this case are going to be nodes that cut across the cyclic molecule. So they in fact are like angular nodes. So when I look at the very first case, I'm going to have a smear of p orbitals that are added together. And in fact, what I'm looking at is kind of like the top of a donut. So it would look something like that with no angular nodes. Now, I should clarify that if I were to look at this edge on, so if I were to somehow draw this cyclic molecule, so this is the plane of the cyclic molecule, and here is that top that I just drew. Okay, I am looking at a donut of pi electron density, but below this plane of the molecule there is another donut, and this one is the negative lobe of those pi orbitals. All right, so basically what I have is a pi donut. That's what would be below this thing here that has no nodes. All right, so I hope that this picture makes some sense to you. But what I'm trying to describe is a three-dimensional object, and I'm limited to 2 dimensions on this sheet. Now, what would it look like if it had just one node? Okay, so in this case, if I've got a circle and I'm going to make one node in it, I might draw a node like that. And so the way this would look if I'm drawing the p orbitals combining in a linear combination here, it might look like this and like this, but because it's a node, these two have to have opposite sign. All right, so we'll have, positive sign node over here and negative sign node over here. All right, is this the only one I can make that way? Well, I want to persuade you that in fact, if I've got 2 molecular orbitals here that have one node, that I can create two molecular orbitals that are orthogonal to one another with that one node. And I realize that this is going to be a tricky argument to make, but I'm going to try to persuade you that in fact if I were to draw that one node perpendicular to the first node, I would create a pair of lobes above and below the plane of the molecule that have basically, say, the positive one up here and the negative one down here. Now, can I persuade myself that these two are orthogonal to one another? Well, imagine if I were to overlay, that is to say, make the product of this molecular orbital with this molecular orbital. All right, if I did that, I would end up, and I'm going to do this in red, just so it's visible. If I were to take this lobe and put it on top here, it would be something like this. Now what I want to emphasize here is that this lobe is half covering a positive lobe and half covering a negative lobe. So when I multiply those together and add them up, as I am in the case of functional orthogonality, these two would be orthogonal to one another. This would add up to 0, as would the one down here add up to 0. So in fact, these are 2 different orthogonal representations of molecular orbitals that have one node. All right, what about 2 nodes? Okay, again, I'll draw a picture here, and I'll draw 2 nodes, which would basically be 2 nodal planes cutting this cyclic molecule into quarters. So I'll have one lobe up here, one lobe down here, a third lobe here, and a 4th lobe here. And if this one's, say, a positive lobe, since we've got a node here, this one must be negative, so this one would be positive. And in my color scheme, I'll have negative lobe here and negative lobe here. All right, so this would be what it would look like. Once again, I can construct an orthogonal molecular orbital to this simply by rotating this, but I can't rotate it by 90 degrees because I'll get essentially the same thing. But what I can do is rotate it by 45 degrees. So now if I redraw this and draw my nodes like this and like this, I'll end up with lobes that are placed around the circle. And again, I'm drawing the tops of the p orbital molecular orbitals that would be here. And let's say there's this one and this one that are positive lobes on the wave function, and this one that are negative. And again, if I overlay these two, we can see that each one of these is half intersecting a negative lobe and half intersecting a positive lobe. So ultimately, these two would show up to be orthogonal to one another. And this is a case of 2 nodes. And I can continue doing this on up the chain. When I get to the very top one, though, now I'm going to be in a position where every p orbital has a node between it. So I'll just do this for, I hope I'm getting this right. Yes, 8 different lobes. So here I've got a node that goes up here, a node that goes down here, one that goes over here, and one that goes over here. All right, I can't rotate this by a small amount to get an orthogonal orbital because I've now divided this the most finely that I can possibly divide it. Basically, I've got individual p orbitals in each of these lobes. All right, and so it basically means that the highest order molecular orbital is just going to be the one where the p orbitals are all set up so that they're alternating in their phase. That is to say, I've got a set of p orbitals that as I go around the circle, I've got the first one is got the positive end up, the second one the positive end down, and so forth. So there are nodes between every pair of carbon atoms, which means there are no pi bonds in the molecule in this. This is a total pi star orbital. And these others are varying orbitals of different kinds depending upon the total number of atoms. So what this tells us is that these same concepts of nodal patterns can explain, for example, why we have this particular set of degeneracies among the energy levels of a cyclic molecule. But the result that we get out of solving this secular determinant gives us a very different pattern of energy levels from the one we get for linear polyenes. And that's something that we can actually observe in real molecules.